Yeah.
Okay, it's now recording. We're set. Okay, so let's take a look here. We're going to kind of wrap up section 2.2, which is basic differentiation tricks, the rules that we're going to talk about. We'll get into some more advanced ones here real soon. And then we want to take a little more advanced look at what derivatives mean, practically speaking. Think of them as rates of change. They're very useful. So we learned this trick. What is this trick? In general, this is one way to say if I want to take the derivative of this stuff with respect to x, that's how we'd say that. So the dx on the bottom is telling us, it's like saying, in a way, and we'll get more refined about this, but it's like saying that's the variable that we're doing this operation with respect to. Like, for example, if we were, in past years, we've done things like this. We would have said f of x equals something, x squared or something like that, right? And so if we were going to expand something out, what if f of x equaled the quantity 2x minus 1 cubed? And we wanted to expand that out. We're expanding it out for the variable x in this case, right? That's kind of like what we're doing up here. We're specifying that we're going to do this derivative thing we're talking about, where x is the variable. Okay? So once again, the way we say that, the derivative with respect to x of the quantity cx to the n, or even better, the derivative of the quantity cx to the n with respect to x. Now, what was our formula for that? We called this the general power rule.
So this cnx to the n.
Yeah. Well, all we did was, if n is just some real number, it doesn't even have to be an integer, and c is just some constant, right? Then we're just going to bring this exponent out front, multiply it by the coefficient, and then what do we do to the power?
Take it to the n minus 1.
Yeah, subtract 1. And so we end up with something like that, right? Okay, so
Yeah, there's some.
there. Okay, so then how about, what's that?
What do you mean? What's it?
What's that mean, first of all? Okay,
Over.
yeah, and what are we doing here? We're taking what? Okay, how would we say that? What am I asking you to do?
Well,
I'm
you
asking you to
aren't
take the derivative of
X.
x with respect to x, okay? And if we apply the general power rule, that just looks like, this is what Nolan was doing, that just looks like, it's like saying if y equals x to the 1, then y prime, another way of saying the derivative, it's got all these fancy, they all mean the same thing. Y prime is the same as dy dx, same thing. That's equal to, if I bring the 1 down front, 1 times x to the 0, right? Technically, what's anything to the
1.
0 power is 1. Right? Okay, so the answer is 1. Nothing there.
Fail.
Okay, so our answer is 1. There's another way to look at that. Look at this even just algebraically. The derivative of x with respect to x, I could write that as dx dx.
Yeah, that's one.
Now, it's not accidental that dx divided by itself is 1. Okay, it's a completely different way of looking at this. And later on, we'll actually kind of look at graphically what did that mean. But algebraically, that's still just 1. Either way you slice it, the derivative of x is 1. Okay? Now,
We're ready.
real quick, I just thought of something else maybe I want to throw in there. Because this can't be very clear to you why that's significant that those two things are the same. What if we took an example like this? What if I took the derivative with respect to t of x? That's not 1.
No, it's not.
That's not one, because that's dx over dt. That's something weird. What that is that. It's the rate of change of x with respect to t, really. If I had something graphed that had x's on the vertical axis and t's on the horizontal axis, that would represent the slope of that curve at whatever point I chose. Okay? Just like when we say something like dy dx, that's the change in y over the change in x. That's the derivative of, or the slope of, the function y equals whatever the function is. Right? Okay, so for example, what if we had this? What if I defined y equals x cubed? Then dy dx is what?
3x squared.
3x squared, right? That's the same thing as saying the derivative with respect to x of that, because that's y. It's just notational trickery. It doesn't mean anything significant, but I want you to be able to just to realize when you see these things to not get confused. They're just saying the same thing. Okay, that'll get a lot clearer as you work through problems. If it's at all murky now, it won't be. I promise. Okay, so looking on here, what about that one?
We don't have an x.
You're right.
So
I don't have an x. So what am I going to do about that?
isn't that just a line?
Well, you could look at it that way. If I want to find the slope of that function, if I take this as a function, that's the function y equals negative 77. What's that graph look like? Horizontal line, y-intercept of negative 77. What does derivative mean again?
Slope.
Slope. What's the slope of that line?
Definitely.
Yeah, 0, right? It's a horizontal line, so the slope is 0. So that's one way to think of it. The answer is 0. We know it's 0. What's another way you could defend that answer?
Let's do the first power. So.
Now, if I want to write this as a function of x, negative 77, if I want to write that as a function of x, that's the same thing as negative 77 times x to the...
First.
No.
Oh, 0.
0. Yeah. Right? And so if I differentiate that, when that 0 comes out there, what's it going to do?
0.
Yeah. 0 times negative 77 is automatically going to give us our 0, isn't it? So even if I did try to apply this general power rule, it is going to give me that answer 0. Do we want to do that every time? No. In cases like this, where I'm just differentiating x, there's no sense going through that whole hassle. We just know that the derivative of x with respect to x is 1. Right? If we're ever differentiating any constant, what's the answer always going to be? 0. Yeah. So that's a general rule also. So we could, if we want to, I think they even do in the book, we could put a box around that and call that a standard form if we want to. There's another one, right? They're pretty simple ones. Right?
Wait, but if it's the same as the...
So when derivative of x with respect to x is 1, derivative of a constant with respect to x or any other variable, 0.
Always.
Okay.
Always.
Yeah. Okay, what about that one?
Well,
Try that. Try that real quick. I want to know what's the derivative. There's y. I want to know what dy dx is.
slope.
That's just yet another way. We got a ton of ways to say derivative. I can say dy dx, y prime, f prime of x, derivative with respect to x of whatever the function is. Because they all have subtly different flavors to them that we'll see.
I just like one.
Do you?
Yeah. Yeah, and that's tacos.
What? I don't understand.
So they do, those are all different ways of saying the same thing. Okay. Now, is that a form? We only know, really, we know very little at this point. We know essentially one rule, the general power rule, and we know a couple specific cases that we just know the answers to because they're so easy and common. But how can I make that fit, that power rule?
Pull your fraction out.
What fraction?
2.
Oh, okay,
Which
but
is x to the negative 1.
oh, okay, good. X on the bottom is the same as x to the power negative 1. So I've got to write this. I have to be able to write this in that form for at this point in our calculus careers to be able to do the derivative. That's the only show and count. That's the only thing we can do. So I've got to be able to write it in that form. And so a lot of times you might call this pre-writing the function. Before you even do the calculus, do the derivative, you got to write it in a form that makes sense. So this one's going to look like
2x to the negative 1.
2x to the minus 1. And now we can apply that rule. So what's our answer?
Negative 2x to the negative 2.
Bring the negative 1, multiply it by the coefficient. So that gives me my negative 2, x to the negative 1 minus 1, negative 2. Now if I want to simplify that, maybe and write it without a negative exponent, what would that look like then?
Negative 2 over x squared.
Because a negative exponent on the top is the same as a positive exponent on the bottom, right? Okay. What about that one? Okay, that's just another way of saying derivative, isn't it? If this is f of t, then f prime of t means the derivative of that function.
Maybe just make this t.
Okay, but how are we, I mean, yeah, you can almost do that one directly, but what are we sort of doing in our heads there with that 4 and the 5? Yeah, we're just pulling the fraction out front. Even if you don't write this out, you're thinking of it this way. 4/5 times t squared, right? And then when I differentiate, I'm going to multiply that 2 times the coefficient, which is going to give me 8/5 t to the 1. Yeah.
Go back up to 0.
Previous slide.
You just multiply the power. Okay, I got it.
Okay. Okay. Okay, what about that one? Let's one back.
Oh.
That one. Looks scary, but once again, if we just, our goal is can we make that look like something times x to a power? Okay. Yeah, okay, there's the part. The 5/2 is probably not a big deal. There's our coefficient. But now what about the x? I know I'm going to get x to some negative power because it's on the bottom. How do I say the cube root of x squared?
3/2.
No,
2/3.
2/3. Remember, whatever number sits on the radical, the index of the radical is the denominator always. So, that, right? Okay, so now everybody just do this, try this on your own real quick. Kind of close, in a way.
Inverse the most.
Make 5/3 times x to the negative 5/3.
Yeah, that's what I got.
Okay. Okay, so let's look at that. So I'm going to bring my negative 2/3 out front. I've got a 5/2 times negative 2/3 times x to what power? Okay, good, because negative 2/3 minus 1 minus 3/3, right? Negative 2/3 minus 3/3 is negative 5/3. So now we can do some stuff. We can simplify this a little bit, right? The 2's cancel, so I get a negative 5/3. There's our coefficient. And then x to the negative 5/3. How could I write that, say, as with no negative signs and writing it with a radical?
Cube root of x to the fifth.
Okay, so I got a negative 5 on the top.
3 cube root of x to the fifth.
So then I got a cube root. Right? If I wanted to write it that way.
Well, if you did.
If I did. Okay, what about that? Try that.
Flip the page.
So I'm going to have to do some stuff before I can take a derivative. I've got to simplify that so it looks like a constant, a number, times x to a power, right? Okay, what's that going to look like? What do I do with that quantity 2x cubed on the bottom?
Expand it out.
Yeah, I guess what we're asking here is what's this? If I have a product to a power,
8x to the fifth.
what's the rule that applies to my rule of exponents? Property of exponents.
Distribute x on it.
Right? So then I'm going to get 5 over 8 x cubed. This 2 cubed is 8, right? So that just looks like 5/8 x to the
Negative 1.
negative 3. Okay, so then what's the derivative? Y prime would equal,
Negative 15 over 8x.
okay, and if I want to put that x on the bottom, I can. Like that if I want to. Yeah, right. Okay.
Is there some sort of pattern when you have that?
What do you mean?
That's like what we got on the last one. Except for the only the coefficient and the exponent change. Never mind.
I think it's just probably because when I was making these, I wasn't making them different enough. Okay, what about that? What do we do if we've got a sum of terms like that? Now, when you look into 2, there's going to be a theorem that addresses this, but there's an easier way to say it. When you differentiate a polynomial or something like this, if you differentiate a sum of terms or a difference of terms, you can always differentiate term by term. It's an easy way to remember that. So in other words, I can break this up. Instead of one really ugly-looking big derivative, I can break that up into 4 separate small derivatives. Just differentiate each term by itself, which is really common sense. I mean, that's probably the way you would anticipate doing it. So then what's this first one going to end up being?
The derivative?
Yeah, derivative of the first term.
Negative 2x to the third.
Okay, so I'm going to bring the 4 down and get negative 4 over 2 is just, whoops, it's just negative 2 x to the third, right? What about the next term?
That next variable.
Next term.
Negative 2.
Good. Okay, because the derivative of x is just 1, and then
Nothing.
derivative of the constant is 0, so that's it.
That's cool.
Okay. Okay, so now, what about sines? Let's take a look at this one. The derivative of sine x. We want to come up with a new standard form, a new derivative rule that we can use. So we got to go back to, in order to come up with our trick, we got to go back to limits for this. Right? So what's that going to look like? If I take my general form of a derivative, right? So we know that f prime of x equals the limit of what? X plus, I'm going to call it h, x plus h minus, so I have to write delta x. Well, that's what we're going to learn. We're going to learn the trick. We have to prove it. We have to derive what's our trick going to be. So if we plug that in, then what are we going to get for sine? What's the sine? If f of x in this case is sine x, what's f of x plus h?
Sine x plus h.
Sure. Whoops. Sine of x plus h, right? And then minus sine x all over h, right? Okay. Now, if I can't evaluate that directly because I get 0 over 0, right?
Correct.
So I've got to do some stuff. Okay. Well, what can I do? There's a trig identity that we can use there.
Sine x squared, somewhere out
Okay.
there is 1, isn't it?
I never remember what it is, but I can tell you how to figure out what it is pretty easily. It's on your sheet.
Have off the sheet.
Okay, but let's just we have to come up with the answer to this, don't we? We need to know what is sine of a plus b, let's call it. I can never remember which one that is, but here's how you can always tell. What is the sine of 2x? That's one I do know. That's a real common trig identity. You know what that one is? Very good. 2 sine x cosine x. Now, I know that the answer's got to be something like this. It's either got to be, whenever you do the sine or the cosine of a sum of angles, it always looks like this. It's either going to be sine A, sine B, and then cosine A, cosine B, or it's going to be sine A, cosine B, cosine A, sine B. Okay, now
What is the middle then?
in the middle, I can never remember which is which. It's always either a plus or a minus. Okay, which one does it have to be? If A and B are both x, which one of those is the only one that could give me the right answer?
Plus.
Okay, but the top or the bottom? No, the top's
No,
going to
the
give
bottom,
me
the bottom.
bottom, right?
Yeah.
Top would give me sine of x times sine of x. That would be sine squared x and cosine squared x. Well, that's not what I get.
Yeah.
Have to be the bottom one, and what does the sign have to be? The operator. It's got to be a plus, doesn't it? That's how I always remember it. I never wasted brain cells to actually remember the formulas. I actually kind of did know that one, but if I did forget it, which sometimes I do, that's how I would get it, right? So then I know that this is our formula. The sine of A plus or minus B is going to be sine A cosine B plus or minus cosine A sine B. So we keep whatever that sine is, and we split cosine sine, or sine cosine, cosine sine. Okay? So if we go back to this other page then, let's use that. Right? So that just looked like, oops.
Oh, fuck.
There, that page. Okay, so let's, all right, so doesn't that give us that? Right? Right, because instead of A and B, we've got X and H.
Yes.
So sine of the first one times cosine of the second one plus vice versa. Okay, and then of course just minus sine X. Okay, that's better. That's better. Now what? Maybe I want to try putting H in. H equals 0 and see what happens. Unfortunately, it doesn't work. I still get 0 over 0, don't I? because cosine of 0 is 1, sine of 0 is 0, so that term would disappear, and I'd get sine x minus sine x on the top. That's still 0. So I got to do that. And if I'm thinking ahead here, if we remember back to chapter 1, when I had trig limits like this, the only way I was able to resolve that indeterminacy and get rid of it was to use one of those two special limits that we had, right? Limit of sine theta over theta as theta approached 0 was 1, right? And the limit of 1 minus cosine theta over theta as theta approached 0 was 0, right? Those were the two that I was able to invoke and get rid of the 0 over 0 nature. So those have got to pop out here at some place. What can we do to that numerator up there, do you think? And we're always looking at factors if we can. Can you see? Doesn't look like there's anything I can factor out of all three terms. But is there something I can factor out of maybe two terms? Sine x,
Yeah.
sure. Yeah, sine x. So why don't we do something like this? Right?
Ooh, that's 0.
See what we did? So we're going to take, we just took these two terms, so there's a sine x in this guy and in that guy, and let's just put both of those together and factor out that sine x. If I factor out a sine x, I'd be left with cosine h minus 1, or if I factor out a negative sign, negative the quantity 1 minus cosine h, right? So sort of combine two steps there.
Say that one more time. I was writing.
So, okay, so what I've really done here, I guess, is I factored out a negative sine x. If I divide a negative sine x out of this term, I'm left with a positive 1. If I divide a negative sine x out of this one, I'm left with a negative cosine h, right? Because factoring out is just like undistributing or dividing. Yeah, and you can see if I redistributed that, negative times negative gives me positive, right? And the reason I did that was just to avoid a step. So now this one ought to look pretty familiar, this part right here, right? Yeah. Yeah, so we want to maybe change this just a bit. We could split these apart, right, into this half and this half, each of which has a common denominator, right? And then look what we get for this one, right? Or for this guy right here. No, for this guy. I could factor out, being as I'm taking the limit as h goes to 0, that has no effect on the cosine at all, does it? Right? So I can do what in calculus or in algebra we talk about is just pulling the cosine x out in front of the limit, because the limit isn't acting on it. The limit is only acting on h's, right? That way we can see that we're splitting them into two parts, the cosine x times the sine h over h. Now that's a limit that we know, right? That's 1. So there's that one, right? Okay, now what about the other part? Well, over here, I could split that into a sine x times a quantity 1 minus cosine h over h. I'm going to lump the denominator with that factor in the numerator, right? And that's also a limit that we know. That one is 0, right? That's our other special limit. The limit of 1 minus cosine h over h as h goes to 0 is 0.
So is there a derivative of cosine x sine x?
No. I'll just tell you that one. We could derive it in an analogous way.
Okay, what is it?
It's negative sine x.
Okay.
And we could do it also, but we won't. If we'd have done 1, that's good enough. See how we get that, though? Okay, now we did it, though. We found the derivative of sine x by using the limit, the actual pure definition of a derivative, the limit definition of a derivative. So now we've got another trick. In fact, we've got 2 more tricks, so I'll give you one for free. We get the derivative with respect to x of sine x is cosine x, and the derivative with respect to x cosine x is negative sine x. Okay, and so we can use those now. We got two more, so we got three derivative rules that we can use now. Okay, do I need, anybody want me to leave it on this page for a second, or we can scoot up a little bit? Right there.
So what's derivative of tangent x? Those are two.
The derivative of tangent x is secant squared x. We don't get to that for a while though.
Okay. What about
Secant x, secant tangent x. Derivative of secant x is secant x times tangent x. Derivative of cosecant x is negative, derivative of cotangent x is negative cosecant squared x. Derivative of cosecant x is negative cosecant.
Okay, we're good.
There's not that many of them. You'll know all those. You're going to know about 16 or 20 standard forms. You'll know them like the back of your hand by the end of the year.
I don't know the back of my head.
What's that?
Yeah.
Yeah, that makes sense.
I don't know. You don't ever just sit and study the back. Okay, so we ready?
No.
This will all be on the notes. You don't have to write all this stuff down. Okay. What about then? Take a problem like this. Find the points where this function has horizontal tangents.
Okay, that's just zero times the derivative.
Yeah. So there's the one we want to find. How about? We want to find, here's our function, y equals x plus sine x, and I'm restricting the domain a little bit. It's on the domain where x is greater than or equal to 0 and less than 2 pi. Now, if I want to find those points, find the points where the function has horizontal tangents, I probably need to ask myself the question, where do horizontal tangents occur? Horizontal tangents, that means if they have horizontal tangents, I'm saying those are places where tangents to the curve, like for example, if my curve were to look like this, I would get horizontal tangents right there and right there. Right? Those are places where tangents to the curve are horizontal. In other words, places where the curve has a horizontal slope. Well, what's horizontal slope equal to? 0, right? So horizontal tangents occur where m equals 0, but what's our calculus way of saying m? Well, derivative. That's the derivative's job, right? The derivative's job is to predict the slope of the function. So what we want to do then is we want to find y prime and set that equal to 0. That's how we ask the math gods for those places. If we can set the derivative function equal to 0, the math gods will tell us through algebra where that happens, right? So what is the derivative? If y equals x plus sine x, what is y prime in this case? What's our derivative?
1.
1. Right? That's derivative of x is just 1 plus cosine x. Good. Because that's the derivative of sine x is cosine x. Because what's the derivative of x with respect to x?
1.
1.
That's one of the rules.
That's one of our rules, yeah. And that's really just
Okay.
that's one special case of the general power rule, but it's just one that we'll remember because we use it so much. So then we want to set that equal to 0, right? So if we set this derivative equal to 0, then now we can just switch into algebra mode. We've got an equation, 1 plus cosine x equals 0. And remember, x is restricted. I won't rewrite the restriction, but it's on one lap of the unit circle, right? So how do I solve that? If I'm solving a trig equation, how do I solve a trig equation? Well, okay, but so I'm gonna. What do you mean by that? If I had to break that down in some steps. Yeah, okay, I'm going to isolate cosine x. So I'm going to set cosine, if I subtract 1 from both sides, isolate the trig function. Cosine x equals -1, and that's a unit circle question, right? On the unit circle, where is it? Cosine x is the thing. Cosine sine x, y. Cosine x is which coordinate on the unit circle, x or y? X. Good. So where is the x coordinate 0 on the unit circle? Yeah, it's going to be 5. There and there, right? So what are those two places? Where's this? How many radians is that? Or, okay, so those are my x values. Those are the places where that happens. Those are the x values where that happens. Okay, but so we got two answers: either x equals pi halves or x equals negative 3 halves pi. We want the points though.
Why is it negative 3 halves pi?
Because I was just testing to see if you were paying attention. Of course, it's positive 3 halves pi. Very good. Okay. So now we want the points though. We don't just want the x values. We want the actual points in space. So how do I find the y values? If I know the x values, where do I go to find the y coordinates of those points? Do I go to the derivative? Yeah, plug them into what? Yeah, plug them into the original function. That's what tells me the y values, right? So if I plug into the original,
Yeah, right.
yeah.
You said cosine x is -1. You said cosine is x, so shouldn't it be?
Oh, hold it. I did.
Yeah, that's what I thought too.
Whoops.
I was thinking the same thing.
Whoops.
So confuzzled.
Yeah, I would be too. So that was pretty. So I asked you, where does cosine x equal -1? And then I looked on the unit circle. Then I asked the question 10 seconds later. So where does cosine x equal 0? Didn't I? Yeah. That's not what we're looking for. So those aren't the right places.
Those are incorrect.
Where does cosine x equal not 0? Where does it equal -1? Sorry.
At 1 point.
At 1 point. And where is that 1 point?
-1, 0.
I forgot the radians.
Pi.
Okay, so let me get there. Oh, I killed my cert one. Right, so that's going to be, you're right, that's over here. Right, there's where cosine, the coordinates of that are -1, 0, and that's at pi. Okay, there we go. Sorry, yeah, pi.
That seems
Okay,
a little
so we know we get a single point, x equals pi, and if I want to find y, well, I'm just going to plug that in, right? I'm just going to plug in pi for x, and I get y equals pi plus, what's the sine of pi? 0. Yeah. So the point on this curve is going to be at, what did we say it was? Pi, right? X equals pi, y equals pi. Right? And if we graph it, well, let's see what it looks like. If I graph it, let's investigate. Okay, so if I look at,
4 minutes.
oh man, I had something super cool to do. We're just not going to get to it. So we have, what was it, x plus sine x?
Yep.
Okay, and we want to look from 0 2 pi, so let's go 0, like 6, and then 6 2, 8, close enough. Okay, right? And we wanted to find, what were we looking for? Where the
Derivative is 0.
derivative is 0, right? Okay, so we had a horizontal tangent line. Now we found that the answer was at pi, right? So let me graph that point. If I go up here to, let's put a plot, put a point at pi, so 3.14159.
Over 2 minutes.
Come on, you gotta know more reasons than that.
Well, that's going to be good enough for,
Air.
Apparently not.
Oh, you gotta get this one.
Air.
do I have to put that? I think I have to do this.
I don't know.
I forgot how to do this. I think this is how you do it. Oh, come
Oh,
on.
darn.
Pipe
Can't you
down.
just put
Pipe down. Yeah, there it is. So there's our point. That looks about right, doesn't it? Look at that point on our graph. Doesn't that seem like the place where we got the horizontal tangent line? And if I graph the line, we can even see the line. Let's graph it in green. Be Christmas will come early here.
Approximation.
So y equals 3.14159. There it is. There's the tangent line. We got it. Right? Okay. All right. Okay, so that.
That we should know about?
No, but what I want to look at I just want to give you a heads up. Here's what I really wanted to get to. What I really wanted to do was this. I wanted to get to this example right here. Consider this data for the height y of a potato shot out of a potato cannon as a function of time. So if we were given, this is simulated data, but I think it's going to work. I haven't done this yet. I think this should work pretty well. I think this will work great. So here's, we've got some kind of we're pointing at it with a laser that's giving us back data as a function of time here. So we're getting, for given time intervals, after we start the stopwatch, we've got pretty good estimates of the height in meters. What we want to do here is, I want you to do some stuff. I want you to, first of all, what we'll look at tomorrow is I want you to come up with a good model, fit the data, and come up with a good model for a function, for a position function. Y is a function of t. Assuming we have that, here's the part that's really cool, though. I want you to be able to answer some questions. I want you to tell me, how fast is the tater traveling when it is 500 meters above the ground on the way up? How in the world could you do that from your model? How fast is it traveling? I want you to tell me non-graphically, what's the maximum height reached by the spud? Okay? No. That's not going to be it. How do you know? Because these are just random intervals. You don't know that you caught it right at the very top. Right?
But you can find that out.
We can find it out.
We can find its maximum height.
We can find its maximum height from that.
Of course we could.
Yeah.
B equals 0 to is how you do it.
That's actually quite true.